In this lesson, we will concentrate on the regulatory requirements for the Class B single-engine aeroplane in the climb. These regulations are only applicable to operating the single-engine aeroplane in the commercial air transport category. The takeoff climb requirements for Class B single-engine aeroplanes are stated in JAR Ops 1. But again, as for the takeoff requirements, the climb regulations can be found in the CAP 698 on page 6, section 2. At the top of the page, under point 3.1, we read that there are no obstacle clearance limits or minimum acceptable climb gradients. Let us break down the two elements in this statement. Firstly, the regulations are saying that there is no requirement for a single-engine Class B aeroplane to demonstrate that it can clear an obstacle within the takeoff flight path. Now, other classes of aeroplane have to demonstrate that obstacles within the takeoff flight path can be cleared by a set limit of 50 feet or 35 feet. It seems strange, then, that there is no regulatory requirement for obstacle clearance in the case of a single-engine Class B aeroplane. But surely the idea of the regulations is to enforce a safety margin. What must be understood here, though, is that the pilot of a Class B single-engine aeroplane must, at all times, have visual contact with the ground. Consequently, the pilot will at all times be able to identify the obstacle within the takeoff path and therefore avoid it. However, you may judge that it would still be prudent to carry out an obstacle clearance calculation if there were known obstacles in the takeoff flight path. The second part of the regulation states that there is no minimum acceptable climb gradient for a single-engine Class B aeroplane. Again, this seems strange. The idea of the operational regulations is to enforce a safety margin. However, the reason why there is no operational regulation on the climb performance is that the certification specifications for this type of aeroplane, as stated in CS 23, are stringent enough on their own. In fact, the requirements state that for land planes whose maximum weight is less than 2,722 kilograms, the minimum steady climb gradient for certification is 8.3%. For land plane whose mass is more than 2,722 kilograms, the minimum steady climb gradient for certification is 4%. Even though there is no operational requirement for a minimum climb performance, it would not be safe to operate the aeroplane in such a manner that its performance is so poor it is barely able to climb. Therefore, it is important as a pilot operating this class and type of aeroplane to know what climb performance would be achieved so that the aeroplane will at least be able to climb sufficiently. Provided in most pilot operating manuals or aeroplane flight manuals are climb graphs that help the pilot to calculate the gradient of climb. Such a graph can be found in CAP 698 in section 2, page 7, an excerpt from which is shown on screen. As with all graphs, before you use it, ensure you are familiar with the associated conditions of that graph. In this graph, the throttles are at maximum, mixture is rich, flaps and gear are up, and the cowl flaps set as required. The climb speed for the graph is taken to be 100 knots indicated airspeed for all masses. Working through an example, let us assume an outside air temperature of 30 degrees Celsius and an airport elevation of 2,000 feet. Find 30 degrees Celsius on the temperature axis as shown here. Then move vertically upwards until the pressure altitude line of 2,000 feet is reached, as shown here. Then move horizontally to the right and stop at the reference line here. Now we must enter the weight of the aeroplane. Let us assume a weight of 3,300 pounds. This is shown here. From the point on the reference line, travel along the sloping guidelines until you hit the weight line. Once you have done this, travel horizontally to the right and pass through the rate of climb, but stop before passing through the true airspeed section. You can see that the rate of climb is 1,210 feet per minute. To calculate the gradient, let us assume a true airspeed of 120 knots. So travel up the sloping guidelines until 120 knots true airspeed is reached. Then pass horizontally through the gradient information and read off the gradient of the aeroplane. In this example, the gradient is 9.85%. There will be two main uses of the climb graph. The first main use of the graph is to calculate the time to climb to the cruise altitude. For this, the pilot would need to know the cruise altitude and the rate of climb. However, if the gradient from this graph is used for the calculation of obstacle clearance, then the gradient must be adjusted for the effect of wind. This particular climb graph makes no correction for wind. The reason why the gradient must be corrected for wind is because obstacle clearance calculations use ground gradients. That is, gradients measured relative to the ground, and ground gradients are affected by wind. If you need to refresh your memory on the difference between ground gradients and air gradients and the effects of wind, click the Quick Navigation button which is flashing for you. Then go to the General Performance Principles section and then click on the Climb lesson and on the appropriate subheading. There are some example calculations in CAP 698 for you to work through and practice. For example, on page 6, section 2, there is an example on how to calculate the climb gradient using the graph. Just below this, there is another example to determine what the maximum permissible mass is in order to achieve the minimum 4% climb gradient. This maximum permissible mass is sometimes referred to as the MAT or watt limit. On page 8 of section 2 is another example. This is an example of how to calculate the horizontal distance required to climb to a given height. These issues have been covered already in the climb lesson in the General Performance Principles section. This completes the lesson on Class B single-engine climb requirements. Hopefully from this lesson you will have learned what the requirements are and also how to calculate the climb performance so that you can comply with the regulations.